I'm going to be presenting a dynamics problem today, and it is dynamics problem 14.24. Basically, what we have is we have some kind of explosive shell going towards a wall at a at at a point 4 meters away from the wall. It explodes, causing the shell to separate into three fragments and hit the wall at certain locations marked by a diagram, which I'm going to be doing in post editing right about now. Okay. So and basically what we're given is we have the initial velocity of our shell, and then we have the masses of each fragment, and then we have where they hit on the wall. And from this info, we are supposed to find the speeds after the explosion of each fragment. Something that kind of bothered me on this problem, considering there's an explosion, would I feel like that would impart energy into the system and thus screw up, conservation of energy, conservation of momentum, and just all around mess things up. But it's a physics problem, so things are perfect, so we're not going to question it. Um, but no, so let's go and get started. I'll jot down kind of our knowns real quick. It's going to take me a little bit to get used to writing with this, because you're writing in one spot, looking at a different one, so it's a lot different. So we are that's a W, not a V. So we are given um the initial velocity of the shell in vector form. So I'm going to write in slightly different notation. Still vector form. It's just it's a way that I learned back in Cal 3 to write it. It seems to clean up the numbers and just everything you have to write a lot more. So um, okay, so we're given that. We're also given the masses. So sorry if it takes me a little bit to write all this out. I'm getting used to it, so it's gonna kind of. Oh, see, the magics of computer technology allow me to press one single button and erase a mistake. It's beautiful, isn't it? Now, of course, editing out a mistake is a little bit more difficult, so I'm probably just going to leave them. You only have to go to special features to find the bloopers. So, just from the problem itself, we are given those numbers, and then we are given some more numbers on the actual diagram. So, we're gonna write those. We're gonna write out. Just gonna put initial coordinates, because they all start at the exact same spot, so you don't have to worry about that being different. Okay, let's scroll a little bit. This is going to take some getting used to, scrolling around and stuff, so there we go. Pen's a little wonky to get used to, so given on the diagram, it has a position of 0 meters in the x direction, 0 meters in the y direction, and then 4 meters in the z direction. And then the final coordinates are going to be separate on each one. So yeah, we'll just leave that as final. So let's look on here. We'll start off with A. My handwriting is usually horrible, so this isn't too much worse, I don't guess. So negative 1.5 meters in the x direction. It did not move in the y direction, and we have a negative 4, or sorry, we have a 0 meters in the z direction, it moved minus 4 meters in the z direction. We could move our axis forward to where, you know, our initial coordinate would be 0, which I kind of like that a little bit more. So let's see, right here, we're gonna actually shift our coordinates a little bit. Let me get my eraser a little bit smaller so it doesn't erase everything. There we go. And so we're going to actually shift our coordinate frame ever so slightly. And this is now -4 meters by the magic of computer-aided presenting. So scroll up a little more, get some more room going. Okay. So then next we have B. And this is going to equal, we go 4 meters in the X direction. We end up going up 2 meters in the Y direction. And the same -4 meters in the Z direction. And lastly, C travels nothing in the X direction. It's still in the YZ plane. It goes down 3 meters in the Y direction, and it goes again -4 meters in the Z direction. Okay, so that is what we're given in the problem. So trying to see if there's a better way to actually view all this, but there's what we're given. So I guess it's time to get started working. So with this problem, we're going to be using the conservation of momentum. Since there's no external forces acting on it, and there are no external forces acting in the direction we're trying to apply the conservation of momentum, and therefore we are allowed to use conservation of momentum, which is stated as or for this problem we're going to have m naught times v naught, and this is going to equal to the sum of the masses and mass times velocity of each particle. So we have ma va, mb vb, and finally mc vc. Okay, we can, you know, go and get the masses taken care of, so that we're left with 6, and then v naught, which I'm going to leave as v naught right now. I'm getting kind of a general equation that I can use later on, because we'll end up splitting it into x, y, and z components. That way we can actually solve for the velocities, and then yeah. So got a little distracted there. Okay, so that's 3va plus 2vb plus 1vc. Okay. So our conservation of momentum equations are as such. Read again. Determine the speed of each fragment. So speed's going to be, you know, the we're looking for the distance over the amount of time it takes. And so, okay, basically we're looking for velocity without, you know, the direction. Well, given here we have 3 unknowns still, but we only have 1 equation. Well, if we break this equation up into each one of its components, because there's a x component, a y component, and a z component of each one of these velocities, then we will end up having 3 equations, 3 unknowns, and therefore being able to solve for each unknown. There's only one problem with that. It will give us our the velocities in a certain direction when we're looking for the total speed. Therefore, we can actually solve for the time, and we can use Pythagorean theorem to actually find the distance traveled from the spot it exploded to where it actually impacted the wall, and we can take that total distance over the amount of time it took it to hit the wall to find our speed. So as such, we'll go ahead and get right to it. As soon as I get this back on track. So we have 6, and then we're working in the X direction. So we have 12 sorry, these are in kilograms, but you know, divide through by kilograms, because you can divide everything by kilograms and you can make it unitless. So, you know, you don't have to worry about that. In fact, well, I'm just not very good about keeping up with units, so these are 12 meters per second, because we're in the X direction, mind you. So this is V naught X, and this is going to be equal to 3 VAX plus 2 VBX plus VCX. Okay. Nextly, we're going to go to our Y, which is going to be, you know, we're keeping all the same masses. In this one, we were given is a total of 9. Let's put that one in parentheses. 9 meters a second. And this is going to be equal to 3 VAY plus 2 VBY plus VCY. And go and scroll a little bit. That way I can see what I'm actually working on. And then lastly, we'll be working in the Z direction. So we have 6 times negative 360, there we go, meters per second. It's going to be equal to 3 VAZ plus 2 VBY plus VC. Oh, there I went again. I was transcribing the deal above and ended up putting the wrong subscripts. And so then we have these equations here, which give us 3 equations, 3 unknowns. But before we continue on, there's a little simplification we can do. Going back to the, let's go and scroll up. If we look back at our distances here, we notice that A does not travel at all in the Y direction, and C does not travel at all in the X direction. Therefore, VCX is going to zero out, and then VAY is going to zero out because they don't actually travel. The total distance traveled in that direction ends up being 0. So, you know, just a little bit of simplification we're allowed to do. Well, we're also able to, okay, so that gives us, you know, our basics to, you know, we can solve for velocities. We can solve for each one of our velocities. Well, okay, so we have velocities in a certain direction. That's all nice. That's nice and everything. We can take those velocities and do one of 2 things with them. We can find from those velocities, we can find the amount of time it takes to travel that distance. Or we could also use, I believe we could also use our sines and our cosines and such of the angle from the z-axis. But that's more complicated than I feel like doing today. So, so we have those equations. We know that VAX is going to equal the distance traveled in the X direction by A over the time it takes A to hit the wall, and so we have that, and so we're able to find that. We also have I apologize. I stated earlier we had 3 equations and 3 unknowns. I was mistaken. We have 3 equations, but we have a total of, I believe it is 7 unknowns. Because total of 7 unknowns, so we're not actually able to solve. But by relating the velocities in a direction to a distance traveled over a time, we're able to simplify all those unknowns that unknown down to a down to, since basically this is unknown, this is known, and that's unknown, and therefore we're able to simplify that down to a TA. Well, at the same time, they're all gonna a piece is gonna hit the same hit the wall at the same time as it's gonna hit the wall, because it's the same piece, and so we're able to find a common variable, which is our TA here, and use that to actually condense down our number of variables down to 3 variables. And again, we didn't have to use the velocity of a in the y direction because it ends up being 0, so it's 0 divided by anything is 0, so it's pointless. So next we have b, which is going to have a component in each direction. So I'm just going to kind of jot this stuff down real quick. And v bz equals zb over t. Okay, go ahead and scroll down a little bit more. There we go. Apparently I had the touch on my oh, I just hit the bottom of my little deal, so I'm about to go up and go back to the top, so we'll go and get this jotted down real quick. We have VC, what is that, VCX, which is non-existent, so that's not the one. VCY, there we go. Y sub C over T sub C, and then we have V sub C Z equals Z sub C over T sub Z, or T sub C. I'm getting myself tongue-tied. Okay, and so we're just going to kind of scroll over a little bit. Getting used to all this stuff. Okay, so given those equations, we're able to plug everything in, basically simplify everything down, given what we found from the picture, which we have over in our givens, and we're basically able to simplify this down to oh, a part of my math is wrong, so I'm gonna have to actually break out a calculator. It's been kind of a long day, so we have, what is that, 6 times 12, 72. That checks out. So we have 72 is going to equal a negative 4.5 over TA plus 8 over TB. Our next one, we have a 6 times a negative 9, which is going to be a negative 54. And that's going to equal to 4 TB minus 3 TC. And lastly, this one's going to be the one I actually need a calculator for. Give me just 1 second. I'll be right back. I should have a calendar, calculator. Well, I seem to have misplaced my favorite found my favorite calculator. Oh. There we go. Sorry about that. Some of the math I did earlier, I wasn't paying attention when I did and copied the same number when I wasn't supposed to, but we have 360 times 6, which is going to give us a negative 2,160. That's a large number. So, negative 2,160, I believe I said. That's going to be equal to a negative 12 TA minus 8 TB minus 4 TC. From here, it's just basic algebra to get everything rearranged. It's kind of a pain, but we're going to kind of box that off. We have let's see where my mouse is. There it is. We have TA going to be equal to, putting this in fractional form because, you know, less work there. Or, well, not less work, but, you know, more accurate. Don't have to worry about rounding errors near as much. So that's always a good thing. And then that's over 855. And then we have TC is going to be equal to 13 over 1374. And no, this is not from memory. I have it right here beside me, so that wasn't such a good box. Okay, so now that we have our what are they called? Our times, now we actually have to find our distances. We can find that. Yeah. Oh. Okay. Come on, work. Okay. Our distances can be found using these right here, so we'll go ahead and, since we're going from a zero frame, we can put this equals, what is that, square root of 1.5 squared plus 4 squared, square root of 2 times 4 squared plus 2 squared, and then that's going to be 3 squared plus 4 squared. That one's going to be 2.25 plus 16, and then that one's going to be, what is that? That's 1632 plus another 4. 32? Yeah. So that's going to be 36. Hey, looky there. That one's real easy. 6. And then this one's going to be, or I should probably put a little equal signs in there. And that's going to be the square root of 9. That's another easy one because it's going to end up being, that's actually one of the special triangles. The only one I'm actually going to have to grab a calculator for is that top one, because that's square root of 18.25, which is an odd number. Or not odd, but it's a strange number. So as soon as I find the square root button, there it is. And I said 18.25. That's going to end up being, as soon as I find, there's my mouse. So end up being 4.2. Seven, 2, then it's 0, 0, so I'm just going to cut it there. Meters. Okay, so from those and then our times up there, we're actually able to solve for our speeds. So I wish this thing had a zoom function. So we're going to go in here and go to options. You can't actually see me working on this part of it, but that way you can see a little bit more. Okay. So we're going to solve it. So we're going to have SA, SB, and SC. And we're going to have a 4.2. Oh, all those are seconds, by the way. There we go. Just tack that on there. 4.272 meters, that's an M, over, I'm going to do this over 13, and multiply that times 1,312. Here we have 6 times 833 over 13. And then lastly we have 5 times, I believe that's a 1374, yep. And divide that by 13. Okay, for a minute there I thought I forgot to hit record. That would not have been good. Oh, I'm actually running out of canvas. So I'm gonna go ahead and plug these into my calculator because I forgot to do that ahead of time because I was so excited that I actually got the um what's it called, the algebra done. So going round it, to the correct number of sig figs. So this is going to be a 431 meters per second. Second one is going to be, let's see, 833. I'm going to divide that by 13. 384 meters per second. And then this is going to be 5 times 1,375. Divide that by 13. And we're left with a 528.8. Oh, good thing I have that back key. 529 meters per second. And just one quick check to see if that's what's found in the back of the book, which I have pulled up somewhere on the computer. Here it is. Where did it go? There it is. 395. And so their B and my B are off by a grand total of 11. And then their C and my C are off by a total of 1. So I'm going to go back through and look and see what where I think I messed up, or find out if I'm how badly I messed up on that one. Oh, I figured out what I did wrong. That 833 I have written, if we go back here, or actually I have to zoom back in for y'all. Oh, don't want to zoom in that much. That 33 that I thought I had was bad handwriting. It's actually a 55. And then that 4 is supposed to be there. So right here, go ahead and go in here and erase this. Also notice that I have 75 written here when it should actually be a 74. That's what I get for doing calculations on the spot, huh? So we have those, and then plug those back in after, we zoom out, because that's disconcerting how large it is. There we go, much better. We'll go in here and go ahead and, oh, wrong way. There we go. So now, get the calculator brought back up. 6, not divided by, times 855. Oh yeah. I can't type today. And looky there, that's showing, oh, still in eraser mode. That is showing 394.6, which rounds up to 5 meters per second. Looky there. And multiply, go and get the next one brought up, and divide. And again, it corrected our error. So yep, made a small error transcribing one of my numbers over. So yeah, and that is our solutions. Go ahead and go here to, oh, that was not supposed to happen. There we go. All total, this is what we have. Some of it's a little bit harder to read, but we start. Oh, sorry, I was kind of hopped up there a little too close to camera. We start off with our givens. We go through. We use the equation for conservation of momentum. We modify it for the equation. We plug in our numbers. We split it up into its different components, and then we substitute the velocity in those components for distance in the direction divided by the time it took it to hit the wall, to find that way we can simplify those the 7 variables down to a total of 3 unknowns, and then from those 3 unknowns we're able to use those equations, finagle it with algebra, which was a pain, to actually find the 3 times. We're able to take the times, and then use Pythagorean theorem to find the distance of the distance that each piece traveled. Divide that total distance, divide by the total time, and we're left with our final speed. So that's this problem. Thank you very much for watching.